So thank you for coming. So I'm going to talk about palindromes, and this is joint work with Petra Berenbrink, Fredrik Malmund-Tran, and Erfan Sadek-Yazer. So I think we all know what a palindrome is. The only reason I have this slide up is because there's a wonderful palindrome there that I really, really like. So a palindrome is a word that reads the same forward and backward. And here's my favorite palindrome. Stress, no tips, spit on desserts. If there was ever good advice for tipping your waiter or waitress at the restaurant, this is it. So what are we interested in here? We're interested in, given a sequence, a stream, find the longest palindrome, if not find long palindromes. Ideally, biologists are interested in this problem, and obviously in real life nothing comes perfect, and they're more interested in finding palindromes that might have errors in them, mismatches, edits. What we currently have is not that. That's on our wish list, but we're going to look at exact matches. In terms of the length, we're not going to first focus on finding exactly the longest palindrome, but maybe something close to that. And then I'm going to talk about a bit more of an exact solution. I'm going to be talking in the streaming model. So what does a palindrome look like? Well, is there a pointer here? Is the green a pointer? Yeah. Why can't I? Oh, here we go. So a palindrome looks like this. It's a string that reads the same forwards and backwards. It's not as nice as the previous examples. So we would like to view this as first half and then the reverse of the first half. So it consists of two substrings, P1 and P1's reverse. And also another property that we're going to use is a palindrome contains smaller palindromes having the midpoint nested inside it. So our objective is, given this text as a stream, we would like to find long palindromes in it. So what do we exactly mean? Here's a palindrome. Well, here are some smaller palindromes. We would like to find, if not the longest palindrome, find a palindrome with the same midpoint that is slightly shorter. So first I'm going to talk about some preliminaries. A lot of this will be pretty obvious. It's for the sake of, let's say, the students, or just to jog your memory. And then I'm going to talk about two different approximations, an exact algorithm, and very briefly mention a lower bound. OK, so let's formalize these observations that we made. We're going to, every palindrome, or every candidate palindrome, we're going to have candidate palindromes. Every candidate palindrome is going to be defined in terms of its midpoint and its length, which can uniquely define any palindrome. And we're going to look at the stuff that comes before the midpoint and after the midpoint to recognize that something is a palindrome. So notice that this description works only for even-length palindromes. Something like kayak is an odd-length palindrome, and according to this definition, it doesn't even have a midpoint. But there's a very simple fix for that. You just take every letter, repeat it twice, so that makes every palindrome an even-length palindrome. Then all midpoints are defined. Your running time, your space complexity, nothing is going to change. So it's just a little hack. So without loss of generality, from now on, I'll assume all palindromes are even length. So we said that palindromes show a nested structure, and we're going to use that. So here is a shorter palindrome than before. And I have to say, I'm overjoyed that my Max slides, they typically, pictures like that, they get shifted and look horrible. These are actually looking pretty OK. So the green line is always going to denote the midpoint. And we're going to use this nested structure. So we're going to not be able to find, in most cases, the exact palindrome, so find something smaller around the midpoint. And we're going to use Rabin-Karp, Rabin, depending on what we use them. Fingerprints to compare substrings to one another, because obviously we would like to have sublinear complexity, sublinear space. So I'm sure pretty much all of you know about these. These are extensively used in streaming string or sequence algorithms. And the cool thing about Karp-Rabin fingerprints is, I'm actually going to point with my finger. If you have a fingerprint for A and a fingerprint for B, it's very efficient, very easy to make it a fingerprint for the concatenation of A and B. Likewise, if you have a fingerprint for AB and A, or one of the two, you can obtain the fingerprint for the missing one very easily. So they have a very nice sort of modular property, which makes them very useful for this kind of algorithm. It also makes it trivial to keep running fingerprints of sliding windows. And will also, in this algorithm, be, since palindromes have, by definition, a substring and its reverse, inverse, we're going to keep track of reversals of substrings, which is also pretty trivial to do with the Rabin-Karp fingerprints. So this is how you compute them. I'll pass this. So we're going to be using a sliding window model. So we're going to have to drop and add characters to our fingerprint, which is, again, very easy to do with Karp-Rabin fingerprints. So, OK, this is not the greatest way for checking time. OK, so let's look at the additive approximation. So what we would like to do is we would like to find all palindromes in our stream. And obviously, if there are nested palindromes, we're going to ignore the smaller ones and report the bigger ones, with the understanding that if you have a bigger palindrome, all the smaller ones inside it, nested inside it, are implied. So this is going to be a roughly square root of n approximation, where n is the length of your given stream, and it's going to use about that much space. And it's an additive approximation. So we're going to denote, given a substring x, x prime is always going to be used to denote its inverse. So the general idea, what we're going to do is we're going to have some candidate midpoints, which have not been ruled out yet as potential midpoints of long palindromes. And we're going to keep track of stuff that comes before the midpoint and stuff that comes after the midpoint, the reverse of this, and compare this. Of course, there are issues with that because, well, there could be quite a few places that you might have to keep track of. So that's going to be the main challenge. OK, so to be able to determine which midpoints we're going to consider, we're going to have these candidate midpoints. We first start off with short palindromes, because obviously every long palindrome contains a short palindrome inside it. So we start off by saying, OK, if I have a sliding window of size roughly root n, and if it contains, like in its entirety, a palindrome, which has a midpoint in the middle of the sliding window, then that's a good candidate. If it doesn't, there is no long palindrome there. So every time we see something like that, we start by saying, OK, here's a candidate. We'll see if that actually turns out to be a good long palindrome. Any short palindromes, any shorter palindromes can be reported immediately because they are going to fall within the sliding window anyway. So the short palindromes are easy, and the longs, well, we keep track of the shorts that might become longs. So those are candidates. So here's an example. We have a window of size 6. So the green is always the midpoint, and the black here, the thick, OK, the alignment isn't that great, but the black is the current pointer. That's the last one, that last character that we read, and this is how much stuff we're looking at right now. And we detect the palindrome. Great. So this could be a big one. So it has a potential to be long. It takes up the entire window. So later, at some point, we do some other stuff. At some later point, okay, this was where the original window was. Now my window is here. And this is the midpoint that I remember. Now I would like to see if this from B to C, this stuff under the blue braces, is the same as this stuff here. So if it is, we found a longer palindrome, so our palindrome has grown. If not, that's it. The shorter one, the previous shortest one that we had found is the maximal at around that midpoint, and we report that one. So again, the challenge for that is, since we're here, now we need to know the fingerprint from here to here, and that's a lot of fingerprints to keep track of as we keep going and looking at every location. So to reduce that complexity a little bit, we do what's called checkpointing. It's not the most novel idea used in this kind of algorithm it's a discretization, essentially. So we discretize our stream by putting these checkpoints at around root n-ish locations, root n over epsilon. So there is roughly root n of these checkpoints. And now we can actually afford to remember the fingerprint between every pair of checkpoints. And now from there, if you ask me to reconstruct any part of any substring of S, I can approximately do that. And it doesn't take too much space. So we lose some information, obviously, because we're discretizing. How much information we could lose when we were reconstructing any part of this string? You could lose about, well, roughly the distance between two checkpoints, well, twice that, if the bounds of what you want to reconstruct don't fall exactly on checkpoints. OK, so we use these to keep track of our candidate palindromes. How do we do that? For every midpoint, we would like to keep track of, let's say this is a candidate midpoint, we would like to keep track of the fingerprint of the portion from the beginning to this point. And we would always like to have the fingerprint of from beginning to our current location. And this is not really necessary. It's just easier to write on a piece of paper. We would like to store all these fingerprints forward and back. Most of the time you won't need it, but it doesn't have any extra big cost. So I'll just say it that way. OK, so how much space is this going to cost me? So we don't have too many fingerprints because of the checkpoints. So we're actually pretty good with that. So midpoints is not big. It's not a big problem. The checkpoints are not a big problem. The big problem is midpoints. We could have a lot of midpoints as candidates. And if a candidate doesn't die, we have to keep track of a whole bunch of things. It could be up to a linear number of them, and that's going to kill the space complexity. So there's something that we need to do about that. So what do we do, coming back to checkpoints, what do we do with the checkpoints? We use them to grow our palindrome by discrete amounts. So as the palindrome grows, at some point we reach a point that it cannot grow anymore. And then we report its midpoint and the last length where we detected a palindrome. This is going to be an underestimate. OK, so here is a candidate palindrome, the blue box. And how do we grow it? We can grow it at this point. We're currently reading this point m plus d such that the reason this point is special is m minus d is a checkpoint. So we actually know the fingerprint from here to here. And we know the fingerprint from here to here, so we can actually compare the two. So every time we grow a palindrome, the left endpoint of that palindrome is going to be smack on a checkpoint. So they're going to start at a checkpoint. Then if they don't, then we're going to lose this area. So this palindrome, actually the red is the actual palindrome. It doesn't start at a checkpoint, so we're going to miss these blue areas and report the blue as a long palindrome. That's where the approximation factor comes from. So how much are we going to lose? We might lose somewhere up to square root of n. So coming back to the space complexity, the fingerprints are OK. Storing the fingerprints isn't too much space. The midpoints are a problem, because we could have a lot of midpoints. So we should look at what is the situation when we have a lot of midpoints. Is there something that we can do about that? So let's take a look at it, because we obviously don't want to keep track of a linear number of midpoints and all kinds of bookkeeping related to remembering a midpoint. So, OK. If you have a lot of midpoints, what it means is if you take any one point in your stream, there are a lot of palindromes that are possibly covering it, candidate palindromes. So what does that mean? That means that there's a lot of overlapping palindromes. Okay? So the problem occurs when your palindromes overlap in a big way. So what does that mean, that your palindromes are overlapping? Here is an example. There is a whole bunch of overlapping palindromes here. But then you just look at the stream, and it's a very, very regular periodic stream. So is that necessarily so? So this has been studied in pattern matching, and it just is easier to show on a slide. So when you have patterns in pattern matching, if you have patterns overlapping, the same pattern overlapping with itself, it overlaps in a very, very special way. So if you have a pattern, it overlaps with another copy of itself after 3 characters, and it doesn't overlap with itself during the 6th character, and it overlaps on the 7th character. That kind of thing doesn't happen. It's either going to overlap with itself regularly at like 3rd, 6th, 9th, 12th character, or it can overlap with itself at most once. Okay? So it's either periodic or very few overlaps, or a single overlap. So essentially, either your pattern is periodic or it doesn't overlap much. So if the first overlap occurs after the second half, in the second half of your pattern, then it can overlap at most once, and your pattern is not periodic. If it occurs during the first half, you might have a bunch of, you will have a bunch of overlaps, and then your pattern is periodic, and it can be really easily, succinctly summarized. So that's for patterns. What happens for palindromes? Well, similar thing happens with palindromes. It's just messier to write. So the end result is a palindrome, if it overlaps with other palindromes, the overlapping area underneath this bunch of palindromes looks like W, W prime, W, W prime, where W prime is the inverse of W. So it shows a very, very distinct pattern again, which can be summarized very succinctly. So that's good. So we call this a run, and we can use a very small constant space, essentially, to summarize it. So what do we have? We either have short palindromes, which fit into your sliding window. No problem. You might have long palindromes that do not overlap much. They overlap maybe with one more palindrome, and you can just keep track of them in parallel. It's not a big deal. You open 2 different processes and do it. It's really a constant factor. Third case is you have palindromes whose midpoints are close together, and they overlap in a big way. Then they're periodic. Then you compress them. Again, it doesn't take much space. So altogether, it turns out that the space usage is not due to storing these candidate midpoints, but it's due to the really dominating factor is the checkpoints rather than the midpoints. So square root of n over epsilon space for an additive approximation of epsilon square root of n. sublinear. Okay. So this was approximate. What can we do for exact? And this was one pass. Turns out you can add one more pass to make it exact. So the little pieces at the ends of a palindrome, you can keep track of them and check that there is something that you're missing during the second pass and find the length of the longest palindrome and the longest palindrome. Okay? So remember in the previous case, we were just remembering the palindromes that start at a checkpoint. The purples are checkpoints. So this part we were missing. So what we need to now figure out is this turquoise here and this turquoise here. Those were the things we were missing. Are they, in fact, the reverse of one another? And it turns out during the first pass, if you look at really long palindromes and you keep track of the portions around them to the next checkpoint, you can actually do this, and it doesn't require too much space. So it actually doesn't increase your asymptotic space. You're still using the second pass in still root n space, roughly. You can find the exact longest palindrome. Okay. Now, a multiplicative approximation. And the good thing about this is square root of n bothers streaming people a little bit. We would like to see polylog. So this one is indeed polylog. So we would like to get a multiplicative approximation. And the reason we were getting this previous space was because there were so many checkpoints. But when you're trying to get a multiplicative approximation, you really don't need that many checkpoints. Because if your palindromes are long, then you can afford to have bigger additive errors just because you're dealing with multiplicative error now. So what we're going to do is, as the potential length of the palindrome we consider grows, we're going to remember less and less stuff from the past. So we're going to allow ourselves to have more and more error. And this is the technique used in approximation algorithms. So the next picture is going to explain everything. So we're here reading our stream. And the immediate past, we remember the last 4 characters. And now we remember at the next level, 4 characters for every other character. Next one, every 4th character. Next one, every 8th character, every 16th character, etc. So these distances are doubling at every level. So what's the space use? We're going to have 4 checkpoints per level. And we have a logarithmic number of levels. So that is going to be log n. If you add some more stuff, polylog n. The way we treat palindromes is really not that different from the previous one. In fact, we can treat it as a black box. We use the checkpoints as we did before. It's just that they are placed farther and farther apart as you look back into your distant past. So we're going to use the same idea. We can compress the stuff as before. We can use the checkpoints as before. And using the logarithmic number of layers, we are now down to logarithmic space use and a multiplicative error. Okay, I will just quote the lower bound. So this is for the additive error approximation. The square root of n error, square root of n space is a little bit bothersome. As I said, we would like to see logarithmic. Unfortunately, that turns out to be a lower bound for the additive square root approximation. So for that one, that is the best space. There's still quite a few open questions there, so there might be better bounds elsewhere for different approximations, different notions of approximation. Okay. So one thing is recently we actually simplified this quite a bit. The running times, everything, the space usage stays the same, but the exposition is much simpler, but it's so recent that we haven't quite worked out the implications, so I didn't write this down here. The big thing is palindromes with mismatches and edits. Biologists are thinking about the less idealized versions of this problem and similar problems. And of course, they have notions of a lot more complicated shapes as well. They have palindromes, sort of jutting out of palindromes, really, really complicated shapes. So we would like to see just how useful for real life this kind of algorithm can get. And we would like to see other structures as well. And now for my really, really cheesy last slide. Thank you. I know, it's bad.
Any questions for Funda?
Yep.
Yeah. So a lot of this algorithm was you have all these checkpoints.
Yeah.
You're sort of looking back and like comparing at every checkpoint. But are you still keeping track of the substring between each pair of checkpoints?
Yes, you have to do that. That's how we reconstruct pieces of the
Right.
candidate.
So then how does that, do you just not keep track of too many substrings within the checkpoints, or how does that not blow up the space into like
So there's root and consecutive checkpoints,
right.
and you can join them any way that you like.
Okay.
But if things fall between checkpoints, then there isn't much that we can do.
Okay.
So that's why it's an approximation, because we're losing all that stuff that falls outside these checkpoints.
So then somehow you're combining these so that, like, you have a bunch of checkpoints,
Yeah.
but you're remembering the substring in between each pair.
Yeah.
How you're
And
combining it so you're not remembering, like, if it's like n/2 or something, you're not remembering all those characters or something?
You just need to remember the fingerprint and then combine them. You don't need to remember the actual characters. Yeah.
Okay.
Any other questions? Well, thank you very much.